In this illustration, we intend to simulate the formation of a sandwich structure under the air blast loading using the CONWEP method in the Abaqus software. Actually, we intend to investigate the effect blasting of 3 kilograms of TNT on sandwich structure in the Abaqus software. As you observe in this picture, the place of explosion is 100 millimeters above the surface of sandwich structure. In other words, the blast source is at distance of 100 millimeters from the top surface of the sandwich structure. The sandwich structure is composed of one honeycomb core and 2 plates which have been placed above and below the honeycomb core. In this example, since the sandwich structure is symmetric, we will simulate only 1/4 of the sandwich structure into the Abaqus software. I will enter the Abaqus software for simulation. I will click on Create Part. First, I will create geometric shape of the plate. I'll select the modeling space as 3-dimensional, then deformable, solid, and extrusion. Enter the rough size of the tracing page equal to 1 and continue. I'll draw a square. Enter its length and width equal to 305 millimeters. Then I will click on Done and enter the thickness of plate equal to 5 millimeters. I will click on Create Part. Here I intend to create honeycomb core. I'll select the modeling space as 3-dimensional, deformable, then select shell and extrusion and continue. I'll draw a horizontal line. Enter its length equal to 305 millimeters. Then draw a vertical line and enter its length equal to 305 millimeters as well. I'll enter the distance between these 2 points equal to 30.5 millimeters. In the next step, I will click on Linear Pattern, select the vertical line, Done. Here I'll enter the numbers equal to 9 and enter the distance between the lines equal to 30.5 millimeters and OK. I will click on Linear Pattern again, select the horizontal line, Done. Here I'll enter the numbers equal to 9, enter the distance between the lines equal to 30.5 millimeters. Then click on Flip and OK in this manner. I click on Done, enter the depth equal to 51 millimeters. As you observe, the geometric shape of honeycomb was created here. In the next step, I'll enter Property module, click on Create Material. The sandwich structure is made of high ductility stainless steel alloy Al6XN, which is composed of 49% iron, 24% nickel, and 21% chrome. I will select density from the general menu. The density is equal to 7,850 kilograms per cubic meter. Select elasticity and elastic from mechanical menu. The Young modulus is equal to 161 gigapascal and the Poisson ratio is equal to 0.35. In the next step, I will select plasticity and plastic from mechanical menu. Here select Johnson-Cook model. Here a coefficient is equal to 400 megapascal. B is equal to 1500 megapascal. N quantity is equal to 0.4 and M is equal to 1.2. Melting temperature is equal to 1800 Kelvin. And this is equal to 1527 centigrade. Here, transition temperature is equal to 293 Kelvin. That is equal to 20 centigrade. In the next step, I'll click on sub option, then select rate dependent. From here, I'll select Johnson-Cook. C quantity is equal to 0.045. Epsilon dot 0 is equal to 0.001 per second. Actually, epsilon dot 0 is the same strain rate, the unit of which is per second. And OK. Then I'll click on Create Section. Here, select Solid Homogeneous Continue and OK. I'll click on Create Section. From here, select Shell and Homogeneous. Continue. The thickness of Honeycomb webs is 0.76 millimeters. I'll click on Assign Section, select the Honeycomb core. Done and OK. I will click on Assign Section, select Plate, Done, and here select Plate and OK. Here you can observe the thickness of honeycomb webs. In the next step, I'll enter assembly module, click on Create Instance, enter both parts into the assembly section and OK. I will click on Translate Instance, select Honeycomb, Done. First, select this point, then this one and then OK. In the next step, I'll click on Translate Instance again, select Honeycomb, done. First, select this point, then this one, and OK. I click on Linear Pattern, select this plate, done. Click on Direction, select this line, enter offset equal to 56 millimeters. In this manner, as you observe, the assemblage of sandwich structure was done properly. Actually, the sandwich structure is composed of 2 plates and 1 honeycomb, and the plates are placed above and below the honeycomb core. In the next step, I'll enter Step module, click on Create Step, select Dynamic, Explicit, Continue. I'll enter time period equal to 1.5 milliseconds and OK. I will enter Interaction module. Here we should define the interaction between the honeycomb core and plates. In this example, the honeycomb core has been welded to the plates. We will use tie constraint in order to define this interaction. I will click on Create Constraint, select Tie, Continue, click on Surface. Select this surface, done. Click on Surface again. Here I'll select these lines. Well, all the lines were selected, so I'll click on Done and OK. In this manner, the above surface of the honeycomb is welded to the above plate. In the next step, I'll click on Create Constraint again, select Tie, Continue, click on Surface, select this surface, Done, Surface, and select these lines. Well, all the lines were selected. I'll click on Done and OK. In this manner, the honeycomb was welded to the above and below plates. In the next step, I'll click on Create Interaction Property, Contact, Continue, and OK. I will click on Create Interaction. From here, select General, Contact, and Continue, and OK. Here I will save the model. I will return to the assembly module, click on Translate Instance, select Sandwich Structure, Done. First, select this point, then this one, and OK. In the next step, we should determine the place of detonation. As you observe in this picture, the blast occurs within 100 millimeters of the surface of sandwich structure, or in other words, the place of detonation is 100 millimeters above the surface of the sandwich structure. To do so, I'll select Datum from the Tools menu. First, select Offset from Point, select this point, then enter offset equal to 0, 0, and 100 millimeters. In the next step, I will select Reference Point from the Tools menu and select this point. Actually, this point is where the detonation occurs. And the distance between this point and surface of the structure is 100 millimeters. I will enter Interaction module, click on Create Interaction Property. Select Incident Wave and continue. Here, I'll select Air Blast. In this question, we use CONWEP method in order to simulate the air blast. In this method, there is no need to simulate geometric shape of the explosive itself. Also, we don't need to define the properties of the explosive either. We will only need to distinguish the mass as well as the place of the explosive. In fact, CONWEP method is the easiest way to simulate an explosion in the Abaqus. Actually, the CONWEP model is a model developed based on experimental data that is customarily utilized by US Army. Here enter equivalent mass of TNT equal to 3 kilograms. Actually, the mass of TNT is 3 kilograms. Here I'll enter all these quantities equal to 1, and these are related to the unit you will select. Since we have used SI metric system in this question, so all these quantities should be equal to 1. But if you have used any other units, you should start converting them into the present intended unit. For example, if you have been using millimeter system, you should enter these quantities. So here the mass of TNT is equal to 0.003 ton, and in such manner other coefficients would include 1 ton is equal to 1000 kilograms, 1 millimeter is equal to 1000 of a meter, and here 1 megapascal is equal to 1 million pascal. These quantities depend upon the type of units you are using. The most important section here is the mass of explosive that is used, that is equal to 3 kilograms. I will click on OK. In the next step, I'll click on Create Interaction. Here I'll select Incident Wave and continue. First, we should select the blast source. I will select this point as a distinguished place for detonation. Here I will click on CONWEP Air Surface Blast. Select this surface so the explosion will act on this surface. I will click on Done. As you observe, the Abaqus software utilizes CONWEP method in order to simulate air blast. Here I will enter time of detonation as 0. Here we should enter the time the blast will start. As the detonation occurs at 0 time, I'll enter the number 0. Here I'll enter magnitude scale factor equal to 1 and OK. In this manner, the necessary settings for detonation were done accordingly. I'll enter load module, click on create boundary condition. Here I'll select symmetry, anti-symmetry and continue. I'll select these surfaces. Done. Select the boundary condition of Y is symmetric and OK. I'll click on create boundary condition again, select symmetry, anti-symmetry and continue. I'll select these surfaces. Done. Actually, the surface which was selected here is the symmetry plane and the model is symmetric to this plate, to this plane. So I will select X symmetric and OK. I will click on create boundary condition, select symmetry, anti-symmetry, continue, select this surface. Done. Close all boundary conditions of displacement for it and OK. In the next step, I'll enter mesh module. Click on seed edge, select these lines. Done. Enter the number of elements equal to 31 and OK. Then I will select these lines. Done. Consider the number of 5 elements for them and OK. I will click on mesh part and yes. Then I will click on assign element type, select plate, done, put the element library on explicit and OK. I will click on seed edge, select these lines. Done. Consider 6 elements for them and OK. Then I will select these lines. Done. Consider the number of 6 elements for them and OK. In the next step, I'll select these lines, done, and consider the number of 30 elements for them, OK. Finally, I'll click on Mesh Part and yes. In the next step, I will click on Assign Element Type, select Honeycomb, Done, put Element Library on Explicit and OK. Here I will save the model, enter Job module, click on Create Job. Continue. Enter the number of cores equal to 4 and click on Submit. The analysis was done successfully, so I'll click on Result. Here, the deformation of sandwich structure exposed to the detonation of 3 kilograms of TNT can be observed. What you observe here is 1/4 of sandwich structure. If you want to observe the sandwich structure in its complete shape, you should tick on YZ and XZ option. In this manner, here you can observe the sandwich panel in its complete shape. And here you can observe the ultimate deformation of sandwich structure having been exposed to detonation of 3 kilograms of TNT. In the next step, we intend to calculate the vertical displacement in the center of sandwich structure. To do so, I'll click on Create XY Data, then ODB Field Output, and Continue. Here I'll select U3 or the same vertical displacement, then select this node and click on Save. Here you observe the diagram of vertical displacement in the center of sandwich structure that is equal to 141 millimeters in size. Here the unit of displacement is meter, and I intend to convert that to millimeter. To do so, I will select Operate on XY Data, Continue, then select this diagram and multiply that by 1000, and then click on Save As in this manner. Then I will copy and paste that in the Excel software in this manner. As you observe, the maximum of displacement caused by detonation of 3 kilograms of TNT is equal to 141.24 millimeters, and I'll enter this quantity here. In the next step, we intend to survey the effect of detonation of 2 kilograms of TNT on the sandwich structure. To do so, I'll click on Interaction Property Manager. Here enter equivalent mass of TNT equal to 2 kilograms. Actually, the mass of TNT is 2 kilograms. Then I will enter job module and click on Submit. The analysis was done successfully, so I'll click on Result. Here you observe the formation of sandwich panel having been exposed to detonation of 2 kilograms of TNT. Here you see the formation of the honeycomb core, which has been distinguished clearly. Here we intend to calculate the vertical displacement of the center of sandwich panel, having been exposed to a detonation of 2 kilograms of TNT. I will click on Create XY Data, Continue, select this node, and click on Save. As you observe, the maximum of displacement is equal to 111 millimeters. I will select these two columns, copy and paste them here in this manner. Here I'll draw the diagram of detonation of 2 kilograms of TNT. As you observe, the maximum of vertical displacement having been exposed to detonation of 2 kilograms of TNT is equal to 111.5 millimeters. In the next step, we intend to survey the effect of detonation of 1 kilogram of TNT on sandwich panel. Here I will enter the mass of TNT equal to 1 kilogram and OK. I will enter job module and click on Submit. The analysis was done successfully, so I'll click on Result. Here you observe deformation of sandwich panel having been exposed to detonation of 1 kilogram of TNT. As it can be observed, the sandwich panel has been exposed to less damage as a result of detonation of 1 kilogram of TNT, and so has less deformation as compared to detonation of 3 kilograms of TNT. As previously, I will draw the diagram of vertical displacement in the center of sandwich panel. As you observe, the maximum of displacement is equal to 69 millimeters. Here I will transfer this diagram to Excel software. Here you can compare the results having been obtained from detonation of 3, 2, and 1 kilogram of TNT on the sandwich structure altogether. Here the diagram of detonation of 1 kilogram of TNT has been marked out by gray color 2 kilograms, with orange color 3 kilograms, with blue color. The maximum of displacement as a result of detonation of 1 kilogram of TNT is equal to 69.25 millimeters. Here I intend to draw the diagram of maximum displacement for 1 kilogram, 2 kilograms, and 3 kilograms of TNT respectively. As it can be observed in this diagram, the maximum of vertical displacement as a result of detonation of 1 kilogram of the TNT is equal to 69. As a result of detonation of 2 kilograms of TNT is equal to 111. And as a result of detonation of 3 kilograms of TNT is equal to 141. In this table, you can observe the results having been obtained from the article. The maximum of displacement in the center of sandwich panel for the detonation of 1 kilogram of TNT is equal to 69.15 millimeters. For 2 kilograms of TNT is equal to 110.68 millimeters. And for 3 kilograms of TNT is equal to 141 millimeters. And you can observe the related diagram. In this diagram, horizontal axis is mass of TNT and vertical axis is vertical displacement. In the next step, we intend to observe the formation of sandwich panel for all three states simultaneously. To do so, I will click on Create from Viewport menu, click on Create again. Here select Tile vertically. Then here I select Link Viewport option. The left viewport is related to 1 kilogram of TNT. The middle one is related to 2 kilograms of TNT. And the right one is related to 3 kilograms of TNT. As it can be observed, when the mass of TNT increases, more areas of sandwich panel will be exposed to deformation, which can be seen well in these pictures.